Hello everyone, I'm Zhuojun from Tsinghua University, Beijing, China. Today I'm honored to introduce my work, ResType, Invisible and Adaptive Tablet Keyboard Leveraging Resting Fingers to you. So this work aims to solve two problems related to the tablet text entry interaction. Firstly, due to the lack of tactile feedback, tablets suffer from low text input speeds. As the figure shows, physical keyboards have tactile landmarks for users to locate their finger positions without relying on visual attention, thereby supporting efficient touch typing. However, this feature is missing on the tablet touch surfaces, which means that users must rely on visual aids to locate keys, leading to frequent visual attention switches between the input area and the keyboard. The second problem is that the soft keyboard can occupy a large amount of screen space, typically nearly half of the screen on commercial tablets. This becomes problematic when typing tasks highly rely on the information displayed on the screen, such as when chatting, browsing the internet, or describing an image. In such situations, users may frequently need to fold and expand the keyboard, which can significantly disrupt the typing process. And these two problems together result in a poor typing experience on tablets. Now I would like to share two related works that have addressed these problems to some extent. The first is Toast, which uses an invisible keyboard that can adapt to users' input. It uses the last n input words to feed the keyboard position and use a Bayesian decoder to predict words, allowing users to input without locating keys precisely. However, this design requires users to input some words for the decoder to reach the maximum accuracy, and the keyboard cannot adapt to fast hand movements. To address the occlusion problem, another work has explored a low occlusion keyboard. The authors hide most of the keys on the keyboard, displaying only a few keys or lines for users to locate the touch positions. Results show that users can access more information in typing tasks. However, this keyboard does not completely eliminate the occlusion, and users still need visual attention to locate keys. In summary, to address the issues mentioned earlier, we need a completely invisible keyboard to eliminate the occlusion and attention switches. We also need an adaptive strategy to help users locate touch positions. It is worth noting that this strategy must be real-time and must not disrupt users' normal typing behavior. So inspired by how users touch the landmarks on physical keyboards to align fingers, and by our prior work, Typeboard that can prevent unintentional touches on tablets, we present ResType. It adapts an invisible keyboards to resting hands in real time. We refer to this adaptive strategy as calibration in our work. Okay, let's first watch a short demo of ResType. In this video, we showed some core features of ResType, including the unintentional touch prevention, calibration, the adaptive strategy, and how to touch type on ResType. So let's begin. Users can rest hands on ResType without triggering unwanted responses like this. And when users put hands on the keyboard, just like placing hands on the home row of a physical keyboard, ResType will recognize the calibration behavior and adapts the virtual keyboards to hands instantly. So basically, users can touch type anywhere on the ResType. The user can move the hands to the left side of the keyboard and touch type normally, and then move the hands to the right of the keyboard. The keyboard will automatically follow the user's hands. So this is how ResType works basically. And this design leads to three research questions. What is the user's typing behavior and how to detect it? How to decode users' input with calibration, and what is the typing performance of ResType? We then designed 3 user studies to answer these questions. Before implementing ResType, we first followed Typeboard to identify unintentional touches, allowing users to rest hands on the keyboard. Typeboard uses diverse features to train an SVM model, including the area, the shape, pressure, and other geometric features of the touch points. The recognition accuracy is very high, which is up to around 99%, so we use Typeboard directly to implement ResType. Then we designed Study 1 to explore users' calibration behavior. In this study, we did not implement anything. Users just performed typing and calibration alternatively in an imaginary typing task. The system provided no feedback to any operations. We just simply recorded all the typing data and labeled all fingers in each calibration. We thoroughly summarized the statistical frequencies of each touch point in calibration, and also the geometric relationships between the touch points of the calibration patterns, which are shown in this figure. And then we designed a threshold-based algorithm to recognize calibration and to feed the keyboard positions to hands. The algorithms were explained in detail in our paper. We then need to decode users' input with calibration. We designed Study 2 to collect users' typing data with calibration. This time, only unintentional touch prevention and calibration detection were implemented. Users are required to transcribe phrases randomly sampled from the McKenzie phrase set, but we only provided asterisk feedback for each intentional touch event. To evaluate the performance of ResType, we also introduced the ResType static in this study. It has the same features with ResType, except that calibration is disabled and the key positions are drawn on the keyboard and are fixed. We found that the touch points are significantly more dispersive on the ResType, but can be counterbalanced by calibration. This shows that users cannot locate keys accurately if they cannot see the keyboard layout, but it can be improved to some extent by calibration. Then we used the typing data to train a general touch model. The touch model was a combination of classical absolute and relative Bayesian input decoder described by this equation, but with the consideration of calibration. Specifically, after each calibration, the virtual keyboard position would change following users' hands. We use all touch point positions as relative to the calibrated keyboard position, but not the actual touch positions. And at last, we achieved 96.3% and 99% top 1 and top 3 accuracies using the hybrid touch model. At last, we conducted a 5-day long-term evaluation to compare the performance of ResType with ResType static. Please note that ResType static is a very strong method, which has the same unintentional touch prevention and input decoding methods as ResType, except the keyboard is fixed and visible. And at last, ResType maintained the same typing speed as ResType static, even without a visible layout. And it achieved 86.7% input speed of the physical keyboards and outperformed normal tablet keyboards by 13.5%. We further investigated the detailed pros and cons of ResType. First, users made more mistakes on ResType than on ResType static, which means that they cannot locate keys precisely without the keyboard layout. But users spend less time between the gaps of words and barely switched visual attention on ResType, which is significantly lower than ResType static. This shows that users are more focused on the typing task and have less extra physical burden using ResType. The user feedback also revealed that ResType caused lower fatigue to users. Though we've made some useful conclusions of ResType, our work still has several weaknesses. Like ResType currently does not support punctuations, out-of-vocabulary words, and personalization. Since it needs users to rest hand on a touch surface, it only supports 3-state touch surfaces, which is not supported by most commercial tablets currently. However, we believe this design has some useful potential applications in the future. For example, if a tablet or dual-screen laptop can prevent unintentional touches accurately, it can use ResType to support efficient touch typing. Furthermore, ResType has an invisible keyboard, which means it even does not need a script at all. It can be implemented on smart surfaces like tabletops with the pressure sensing ability to benefit anywhere typing or AR/VR typing. We can anticipate further applications of ResType as ubiquitous computing develops further and deeper. Okay, that's all of my presentation today. It's my first year to present my work at CHI, and I look forward to seeing you again in the future. Thanks.